In this section, we're going to look at how different ways we can combine functions. So if we start with two functions, we can combine them in different ways. And so in this first definition, I'm using just two functions, f and g, and then we can combine those using our four basic operations. So on the left side here, this is the notation that stands for the function. So this is our sum function, our difference function, product function, quotient function. And then the right side tells you basically how you're going to find those functions. If you know these two, the sum function is just going to be adding up the two functions. This difference function, you're going to subtract, of course, and subtract in this order to get the correct result. So it's pretty straightforward, just applying those basic operations. So an example, a really common example of like the difference function would be in business when you want to find your profit. So you might you have a function that gives you your revenue, how much money you take in, and subtract your cost. So in business, you might have a cost function and a revenue function, subtract those, and that would give you your profit then. So it's just, writing a new function from two existing functions. And functions are just formulas, right? Okay, so we're going to do that, and then we'll also find the domain of some of these here. And when you find the domain, you're basically just going to take the domain of these two things separately and then find the intersection. Remember, the intersection is where they overlap. So if you have a set A and a set B, the overlap is the intersection, A intersect B. And then one more thing, there's always one more thing to remember, right? We can't divide by 0, so you got to make sure if you are finding the quotient here that you're throwing out any numbers that make this denominator 0. Okay, so let's go ahead. These are pretty basic. Most people have no problem here. Now, notice here I've got three different functions, right? And I want to use the f and the g to find the function f plus g. This is the name of the function, and it's not giving you the input. Well, you still need to have an input, right? So this means find f plus g at x. You could, because the input's not given, you could change it. You could find f plus g at y if you wanted, but that, we wouldn't do that because f and g are in terms of x. So don't be confused because there's no at x there. You're going to include that. And then that means we're just going to find f at x plus g at x. So f at x is the square root of 2x minus 4, and g at x is x squared minus 4. And then we do simplify if we can, and that would just be adding like terms if there are any, but there are not, so this is our final answer. That's it. That's the function. Now it does ask us to find the domain. So let's go back up to the function f. The domain of that function, because it's a square root function, we need 2x minus 4 to be greater than or equal to 0. And if we isolate x, x then would have to be greater than or equal to 2. So the domain of f, I'm going to use this subscript here to represent domain of f, would be 2 to infinity. I'm going to use an interval notation. And then g is just our squaring function minus 4. The domain of that is all real numbers. And then I'll put a g there for a domain of g. Take the intersection. So basically you only want the numbers that work in both parts. That's basically what's happening here. And that's your overlap. Which numbers work in both? Well, only these work in both. So the domain of f plus g will be 2 to infinity. And if I found f minus g, it would have the same domain. You don't need to redo that. It's going to be the same. F times g will have the same domain. Now f divided by g, we'd have to throw out anything that makes the denominator 0. And actually, we're going to do that one, so we'll come back to that in a minute. Let's find f minus h first. So f minus h, we're using this function and this function this time. So again, we need a variable, so we'll use x. So f at x minus h at x, and that is square root of 2x minus 4 minus, now the thing with the difference function, subtraction, make sure you remember to distribute. Don't just write minus 2x squared plus x without the parentheses. You have the parentheses and you'll need to distribute that sign. And no like terms, so this is our final answer. There's nothing else to do. And then the domain of, oops, that's a D, f minus h. We already found the domain of f. H is, just a quadratic here. If you plug in any number, you can square it, multiply times 2, and add it, back to the input. There's no problem with any place where this function wouldn't exist, so the domain there is all reals. That's for h. And we already found the intersection of 2 to infinity and all real numbers. We said that's 2 to infinity. So again, it's this part that is making it so that we can't plug in anything smaller than 2. Alright, f times h then. So using these two functions again, we need an input, so at x, f at x times h at x. F at x is square root of 2x minus 4, and h at x is 2x squared plus x. So you're taking this times this. You can expand that. There's only one term here, so distribute that through. So you could, distribute and write that as your final answer. It would be okay to leave it like this as well. It wouldn't be terrible. If we were finding g at x times h at x, I would for sure expand that. You'd get x squared minus 4 times 2x squared plus x, and distribute, you'd have your 4 terms. Alright, so here's our answer for C, and then the domain, because we already used f and h and found the domain, it's going to be the same. We don't need to redo all that work. Same domain. D, f divided by g at x, means we're going to take f at x divided by g at x. So f at x is square root of 2x minus 4, g at x, x squared minus 4. Nothing there to simplify, so that's our answer. That's our function. Now the domain, like I said, we already found the domain of f plus g, which involves the same two functions, and we said the domain of that is 2 to infinity. Well, what we need to look at now is this denominator. So the 2 to infinity is the restriction necessary to get the numerator to exist, right? But then the denominator, notice that has 2 zeros, 2 numbers that make it 0. If you factor that, you get x plus 2 times x minus 2. So this denominator let me write a sentence here. In the denominator, x can't be equal to 2 or negative 2. Well, because the numerator here, this has the restriction 2 to infinity, we already have satisfied the not equals 2, or excuse me, negative 2, because it's not in there. So we have to just throw out the 2 now. So the domain of f over g, we need to satisfy the original thing, but then we need to take away any other numbers that would create a 0 in the denominator. The only thing left that creates a 0 is 2. So this domain is 2 to infinity, not including 2, versus the other ones that included 2. Okay? It still can't be negative 2 either, but this doesn't contain negative 2, so we don't need to make an adjustment for that. It's already out. Alright, so those are our, that's our algebra functions with our 4 basic operations. Now we're going to look at a 5th way to combine functions, and this is called the composition of two functions. We can compose more than two functions. When we're composing functions, we're basically putting one function in as the input into another function. So in the definition here, the notation is this open circle in between F and G. I'm going to use F and G. Of course, we can use other letters. It doesn't have to be F and G. What does matter is whatever function is on the right side is the one that ends up on the inside. The function on the right ends up as your input into F. It might help you to change that outer parenthesis to a square bracket like that. So this g at x is the input into the function f. Whoops. I don't know why I wrote a g. That's not how you spell function. Function f. Okay? Now, this little statement here, provided g is in the domain of f, well, if you got a number that's not in the domain, of course you can't plug it in. So we need to keep that in mind. And that we'll talk more about that in a little bit. All right, so basically here what we have happening is we have this function g, right? Here's our domain of g. And its input is x, and its output then is g at x. So g is operating on x, you get out g at x. Okay, so here's your range of g. Now, if this output is in the domain of f, that's this part here, then we can plug it into f. Okay, so this range doesn't have to all be numbers that you can plug into f. There's just some portion of it that you can plug into f. So actually, I think what I'll do here is move this so my diagram looks a little nicer. I'm sorry. I'm going to move g at x over here. So it's coming over here. And then maybe only this portion of this, so this circle is the range of g. If you can read that. Sorry, it's a mess. And then this circle here, these are the numbers that you can plug in for f. Domain of f. So as long as this output is falling in that domain, then you can plug it into f. And now you've got f at g at x. Okay, so we're using these circles to represent our sets. And so this is now our output. So in this first example here, I'm going to use f and g. And I say, okay, do this for the number 4. So in this diagram, this is going to be 4. We're going to plug 4 into g, get whatever output we get. That number, as long as it's in the domain of f, we're going to plug it into f and get this number. If we do this in general and call it x, which is what we're going to do in part B, notice here I'm doing it at the value of 4. Here I'm just doing it in general. So I'm going to plug in x. This is going to be a formula that will take this number straight over here. This is my function f composed with g. Now I can only take these guys in here as for the domain here, the ones that, you know, I can get out a number that I can plug in. So that comes into the domain part of it. All right, so this is like our formula that will take us in one jump instead of having to take 2 jumps. All right, so let's do it the example, and hopefully that'll help clear up this idea. So f composed with g at 4. We're going to find f at g at 4. So just using this definition, the x is replaced with 4. All right, so this is my x is 4. I'm going to plug that into g. G at 4, g is the square root of x, so it's going to be the square root of 4. So I've got f at square root of 4 is 2. So this, you know, this was a 4. Now I've got out 2, and now I'm going to plug 2 into f. So this is 3 times 2 minus 2. 6 minus 2 is 4. So 4 comes out. Okay, and those don't have to be the same number, right? It just happened to be in this case. So there's my result, 4. If I plug in something else, you know, get a different result. In B, now I'm going to actually find this function. Here I found a function value. Here I'm going to find the actual function where I have the formula. So I've got f at g at x, which is f at the square root of x. So using x instead of a number. And then the f says to take the input times 3 and subtract 2. So it's going to be 3 square root of x minus 2. That replaced x in the original function. So f composed with g at x is this formula. If I know this formula, I don't need to do the two-step process like I did in part A. I can say, oh, I need f composed with g at 4. Well, I'm just going to plug that into my formula. And notice I get the same result. It just does everything in one step instead of having to get one input, put in an input, get an output, now plug it in to something else. Okay, so that's the same result we had before. Alright, now I did ask for the domain here as well. So, because we can only put in 0 to infinity on this inner part, right? We can't take the square root of a negative number and get a real answer. That's going to be the domain. So usually you can just look at this formula and that will tell you what the domain is. But we have to be a little bit careful about that. We're going to talk more about that. We'll look at an example. So here our domain is 0 to infinity. Basically, the original input is preserved here, so you don't have to worry. You can just look at that final answer because you see that original thing there. Okay, g composed with f. So now notice the g and f are switched around. This is going to change the answer. Now the f at x is the inner part and the g is the outer. So g at f at x, which is g at f at x is 3x minus 2 from right here. And then we're going to plug that into g. So here's g. It's the square root of x. So the square root of whatever the input is, which is 3x minus 2. So there's our g composed with f at x. So again, this is the name of the function. This is telling you how to find the function. Okay, so if you're going to label this, that's what you would do. Notice that's not the same as this. And for the domain, notice that f is a linear function, right? 3x minus 2 is linear. So domain is all real numbers, and then the set of outputs is also all real numbers. But we can't put all real numbers in here and get this square root, you know, existing. It's not always going to be real. So we have to keep in mind that this 3x minus 2, the things we get out here, need to be only the numbers that are bigger than or equal to 0. If we get something negative, then the square root's not going to exist. So if we solve that, we get x bigger than or equal to 2/3. So the domain of g composed with f is 2/3 to infinity. Okay, let's do one more. I need a sharper pencil. F composed with f. That seems strange, right? Because we have the same function. That's fine. We can plug a function into itself. This just means we're going to put f into itself. So f is 3x minus 2, right? So that becomes 3x minus 2. And then we're going to plug that in to 3x minus 2. So the x is the placeholder. This is our input in place of x, right? That was our old x. And then distribute and simplify. So 9x minus 6 minus 2 is 9x minus 8. Alright, so here we had a linear function going into a linear function. Answer is a linear function. The domain for that is just going to be all real numbers. Let's see what's on the next page here. How many more do we have left? Alright, I think let's do E, and then I'm going to take a break. If I don't, you're going to hear my stomach growling soon because I'm pretty hungry. So notice here we have the composition operation twice in there, so there's 3 functions involved. When that happens, you're going to work from the right side, that's going to be your innermost, plug that into G. Whatever that result is, you're going to plug into H. So the H is the outermost. You're going to plug that into G. Here, let's do a square bracket. And then into G, you're going to plug in F. Okay, so this is inside of G. G at this is inside of H. So we work from the inside out. Let me put what the functions are right here. Let's put them up here so we can see them. I don't have them memorized. Alright, so f at x was 3x minus 2. So we got g at 3x minus 2. And g is the square root of x. So we've got square root of 3x minus 2. And now we're going to plug that into h. We've got this absolute value function. And so the x here is going to get replaced with this square root of 3x minus 2. Absolute value of the square root of 3x minus 2 plus 1. Whoops, I meant to make that. I like to, when I have absolute value, I don't want that to look like an 11, so I'll write my 1s like that. Alright, actually, this is a little, it would be fine if you left it like that, but we could actually drop the absolute value here because this is bigger than or equal to 0 and this is 1, so we would never get a negative. So it would be okay to simplify this and write that. Okay, but I'll put or. If you don't notice that, I'm not going to take anything off, but you know, this is actually the simplified form. Okay, so for this one, we are going to need, you know, we have this square root in here. We are going to need x bigger than or equal to 2/3 again, so that this exists. So the domain 2/3 to infinity. Alright, well maybe I'll do one more here, because I want to talk, well I'm thinking about it, about this domain some more here. So here I have 2 different functions. Notice I want to find both orders of composition, f composed with g, g composed with f. As we've seen in the previous example, those are not necessarily the same function. So composition is not commutative, right? If you take a times b, it's the same as b times a. That's multiplication, of course, and multiplication is commutative, but composition is not. So we can't reverse the order of composition and say we're going to get the same result. We're going to find both of these. Let's do f composed with g first. And again, we'll use x as our input. So this is f at g at x, which is f at 1 over x. Alright, so here in f, we're going to replace this with 1 over x. So we got 5 over 2 minus 1 over x. Well, that's not how we want to leave the answer, because we have a fraction and a fraction. So we want to, this is a complex fraction. That's what you call it when you have a fraction inside of a fraction. We want to clear out this denominator of x so that we don't have a fraction in a fraction. So we'll take the top and this numerator and this denominator times the LCD of all these little expressions, all the terms inside that big fraction, if you will, and that LCD is x. And then I get 5x over distribute 2x minus 1. That, you know, 2x and then 1 over x times x is 1. All right, so this is the form we want for the answer. F composed with g at x is 5x over 2x minus 1. Okay, so here's where it gets a little tricky with the domain, because you look at this final answer and you say, oh, well, I can't have x be a number so that 2x minus 1 is 0, right? So 2x minus 1, that can't be equal to 0. Well, that would be, you know, when is it 0? It would be 0 if x is 1/2. So that's not in the domain. Okay, that's true. We can't have 1/2, you know, plugged into this formula. But there's something else. And it comes with the simplifying, the way we simplified this, it disappeared. And so what happened is, notice in the original, before we simplified, we have this 1 over x in here still. And because of that, we cannot let x equal 0. If we plug in 0 up here, there's a point where you're going to get division by 0, and that can't happen, right? So we have to also throw out 0. In the simplifying, that got washed out and you don't see it anymore, right? But you have to keep it in mind, look at every step. Because in the original function you can't plug in 0, you're not going to be able to plug it in here either. Even though this does exist at 0, the reason you can't is from this step. At this step you can't plug it in. So from here, 0 not in the domain either. So what I recommend is look at your function in the final form, throw out anything that makes it not exist, but then also look at it before you simplified. Is there anything else that you wouldn't be able to plug in at that step before you simplify? In the previous problems, we didn't have, you know, the thing we plugged in was fine. There was nothing extra to look at. Or, what did I do with that other page? Or the original expression was preserved. Like I said here, no, sorry, where did it go? Yeah, here, this one, right? That was preserved. It didn't disappear in the final answer. So it was there. You didn't have to worry about it at this step. But watch it before you simplify, and then in your final answer, look at all the numbers that make both of those things not exist. All right, so for our domain, if we're going to write this in interval notation, well, let's write it in words first. So all numbers, technically all real numbers, except 0 and 1/2. In interval notation, that would be negative infinity to 0, union 0 to 1/2, union 1/2 to infinity. Okay, so you should be able to do this if you need to, the interval notation. All right, let's look at the other order. So g composed with f at x is g at f at x. So g at 5 over 2 minus x. So I'm just getting that from the function. Now I'm going to plug this in place of x in g. Remember, g is 1 over x. So this is going to be 1 over this. And now again, I want to simplify that. So it's 1 divided by this. You could just do 1 times the reciprocal. I think that's the easiest thing. It's 2 minus x over 5. So see, if you only look at this final answer, it looks like the domain is all real numbers, because we can always divide by 5. But you have to be mindful of the fact that in the original, this expression right here, x can't be 2. So the domain is all real numbers except x equals 2. Or you can just write except 2. You don't have to say x equals 2. Or in interval notation, negative infinity to 2, union 2 to infinity. So in this case, there was only one number that we couldn't plug in to the domain. Here, let me move that over so you can see it. Okay, well, I'll finish. I think there's 2 more problems. No, well, I guess these are all similar problems. I'll do that in the next video.